Okay, so we're looking at the last topic of this bit of mechanics. We've definitely done some tricky questions. This one is a little bit easier, I think. It recalls some of the ideas that we did in a previous lesson where, oh my gosh, another announcement.
Please come now to the school office. Thank you.
It uses some of the equations that we have previously used for SUVAT equations. Now, I know some of you do physics, so you should know these. We will be doing them in normal maths in a few weeks as well. But does anybody remember what the equations are for them?
V squared.
V squared.
U squared plus 2a.
Good.
S equals ut plus a half at
S equals ut plus a half at squared. And V equals U plus AT. There are some other ones as well. I think these are probably the three that we're going to be using potentially in these kinds of problems. Remember that U was the initial, V was the final, A was gravity, which was 9.8. And we talked carefully about which direction things were going in because they were vector quantities. If something was going up and something else was going down, one of them better be positive and one of them better be negative. I don't really mind which one, as long as things going in one direction match each other. So this is questions involving multiple vertical bounces. This is the more it's kind of like a realistic sort of area of things that you might expect to see. So it's literally a ball that is going to be dropped and it's just going to be left until it just keeps bouncing until eventually it stops. A tennis ball, which may be modelled as a particle, is dropped from rest at a height of 90 centimetres onto a smooth horizontal plane. The coefficient of restitution between the ball and the plane is 0.5. Assume that there is no air resistance and that the ball falls under gravity and hits the plane at right angles. All of that is saying is it's just a ball that is being dropped and it's just always going to hit the floor at right angles and there's no air resistance. The reason there's no air resistance is because we are modelling it as a particle and particles have got no dimension, so there's nothing for the air to even resist against. Okay, so it's going to start like this. Oh, it says find the height to which the ball rebounds after the first bounce. So we're going to drop it from here and it's going to go up to here. That's the thing we're interested in, is how high is it going to go on the second bounce. So we need to work out how fast does it hit the floor with, so we can then work out how fast does it rebound. Now we know for this first scenario of it being dropped from the top down to here, we know that the gravity is going down at 9.8. and we know that it is going to be dropped from the top to the bottom 0.9 meters. So S is 0.9, the acceleration is 9.8. We could do G or we could do 9.8. I think this question will probably us be using 9.8. I'm not quite sure, we'll see how it goes. And what else do we know? What's its starting speed? Its starting speed is 0 because it's being dropped from rest. And we're going to try and find out what speed it hits the floor at. So we know that V squared is equal to U squared plus 2AS. So V squared is equal to 0 plus 2G times 0.9. So V squared is 1.8G. So V is the square root of 1.8G. Now we're going to do part B of the question. I'll give you a chance to finish writing some of that up if you're still writing it down. Okay, so we're now going to think about how high does it bounce for this bit of the journey. So we're going to be thinking about this. First of all, if V is square root of 1.8g, what is U going to be equal to? Not quite.
Oh wait, the restitution half.
Coefficient of restitution is a half, so the value of U will be a half of this. So it's going to be a half times the square root of 1.8g. That's what the value of U is going to be. And what will the value of the acceleration be for this journey? Good. It's going to be minus g because we've now taken upwards as the positive direction because we've given u is a positive number. So we're pretending that upwards is positive now. What do we know about the speed when it reaches the peak? It's 0. When the ball gets to the top height, it completely slows down until it eventually stops, and then it will start coming back down again. So we're going to say when v is equal to 0, and the thing we want to find out is the height to which it's going to rebound. So we're going to try and find out what s is. And we know v squared equals u squared plus 2as. So 0 is, now squaring this, we've got to be a little bit careful here. What do I need to be careful of when I square this? Just make sure you square the half and you square that bit. So when you square a half, you get a quarter. And when you square that, you just get 1.8g. And then you've got plus 2as, which is minus 2gs. So we get 2gs equals a quarter times 1.8g. Yeah, what can we divide both sides by? You can divide both sides by g. I can cancel out the g. And then when I divide by 2, I'll have a quarter. A quarter times 1.8, and I'll divide that by 2, and you get s is equal to a decimal number, 0.225, or 9/40. I'm not sure which is going to be the best one for us to use in this question. Now we're going to have to use that again for the next bit, okay? Because it's saying find the height to which the ball rebounds after the second bounce.
Should be a pattern.
There's going to be a pattern, but I'm not ready to dive in with what the pattern is just yet. I mean, I think we probably should do it the long way, but if you see what the pattern is here, we've gone from 0.9 to 0.225. What do we predict the next one should be?
A quarter of the height.
Yeah, a quarter of the height. Do you see what's happened here? 0.9, if you divide that by 4, you get 0.225. So we're predicting that the next one's height is going to be a quarter of that, and then the next one after that is going to be a quarter of that, a quarter of that, a quarter of that, all the way.
Do they know each other?
Is it because u squared? Is it because of the equation?
It is. It's because here you keep multiplying it by e, but then that is getting squared and it becomes a quarter instead of a half. So that's why it's every time is going to be a quarter. I'm not sure that we should do the long method of us doing it. Should we just say we know it's going to be a quarter, or do you want me to do it?
You should do it.
Should we just do it really quick?
Do the next. And then
Okay, I'll do it really quick. I'm going to get rid of these equations because we don't need them anymore. I'm now going to do the journey from here down to find out what the speed is. So I can say, well, it starts off with a speed of 0. The acceleration is g. The distance it's travelling is 9/40 or 0.225. And we're going to try and find out what its final speed is. So we're basically doing a replica of this side over here. And we're going to end up with v squared equals u squared plus 2as. So v is equal to the square root of 0.45g. Now if I take another colour, and we're going to do for how long it takes to get up to the top here, and I'll do that in purple, we're going to do a replica of the red part. So u will be a half of the square root of 0.45g. A is minus g, v is 0, and s is the thing that we're interested in. So it's a replica of the red part. And we're going to come up with, if I can squeeze this in, v squared equals u squared plus 2as. So we get 0 equals, this thing squared is a quarter times 0.45g minus 2gs. So you get 2gs equals a quarter times 0.45g. The g's cancel, and when we divide it by 2, you get 0.225 divided by 2, which is 0.1125 meters, or 9 over 80. Hang on, I've done that wrong. 0.45 times 0.25. Sorry, I've done that wrong. It should be 9 out of 160. Yeah, that was a half, and I was like, well, that's totally not what we predicted. So it's 0.05625 meters, which ends up as being 9 out of 160. Obviously, those answers you should give to 3 significant figures. You should round them, but for what we're trying to do in this question, it's maybe not that sensible. So first bounce, 0.225 meters. Second bounce, 0.0563. Just notice how I've rounded that to 3 significant figures. Yeah, I actually think it's probably easier to see it in the fractions. That's why I like wrote 9 over 40, and I thought actually because I think it's easier to spot what the patterns are. And I suppose to begin with, we should have noticed that 0.9 is 9 over 10. So we're going to try and find out in part C, this is the part where it gets interesting. It says find the total distance travelled by the ball before it comes to rest according to this model. Okay, so we have got the ball is doing this journey. Yeah, well, we're going to talk about what will happen here because it would, in theory, keep bouncing forever, but just getting smaller and smaller and smaller and smaller. Now, this distance is 9 over 10. Don't know why I've gone purple. I should have done that in blue. This distance here is 9 over 40, and this distance here is 9 over 40. So there's 2 lots of 9 over 40. We're trying to find the total distance that this ball is bouncing along. Now, if we do the next part, there's going to be this one and this one coming down. So there's 2 lots of 9 over 160. And then we've got, again, another journey where there's going to be 2 lots of 9 over 640. Now, there's something that you won't learn about until year 13, and it's this formula that we've got down here. It says the formula for the sum of an infinite geometric series. Now, I just want to quickly break down a couple of these things that you might need here. This is in the formula book. So when you do your UCAS mock exams this year and stuff, this will be in the formula book. S is the sum of a particular series. A is the first term in the series. What do you think R might represent? No, actually R stands for the common ratio, and it's the factor that you multiply by. Like when you have a normal sequence like this, like 2, 5, 8, 11. This is not a geometric series. This is an arithmetic one because it's just going up in the same amount each time. So the one that we're really looking at is 9 over 10, 9 over 40, 9 over 160. Whoops. 9 over 640. So we would say that our first term is 9 over 10, and our common ratio, what are we multiplying by each time? A quarter. Okay, so we now know how to use this formula, okay? We now know how to use this formula. We just need to be really careful about what we're going to plug in, because we are going to try and find out that the total distance that it moves is 9 over 10 plus 2 times 9 over 40 plus 2 times 9 over 160 plus 2 times 9 over 640 plus ... And that's just going to keep going. That's what S is. S is all of those things added together. Now, what would you prefer that I had written at the beginning here? I'd like there to have been an extra 9 over 10, because then it's just the whole thing has been doubled. So there's 2 ways. We can either ignore this one and start our series here and then add on 0.9, or we can pretend that they're all doubled and then at the end minus 0.9 or minus 9 over 10. Which way do you want to do it? Ignore it or keep it and then minus it?
Ignore it.
Okay, let's ignore it. So that means that it is 9 over 10 plus 2 lots of this series that we've got here. And this series that we've got here, which I'll do in this kind of green bit, we're now going to think, what's the first term that we have in this series? Good. So the A is 9 over 40. So I'm going to put 9 over 40. And R is still a quarter. It's still being a quartered each time. So it'll be divided by 1 minus a quarter. So if we just finish this up by typing that all in the calculator, you have 9 over 10 plus, so that's 9 over 14 divided by 3 quarters. So that's 2 times 3 over 10. And that whole thing comes to 1.5 meters. That means it's travelled 1.5 meters. Well, the model never says it stops.
Yeah, because if we can keep carrying on, we can't.
But that's kind of amazing, right? That it's never going to stop, but its distance will never get more than 1.5 meters.
So in a way, it will never quite reach 1.5.
In the same sense, yeah, it will never quite reach 1.5 meters, but it also will never stop bouncing. So this is where we start getting to this weird world of like of infinite things not necessarily making as much sense as we would hope them to. Because every time it's bouncing less and less and less, okay? And I'm not going to do it that alternative way, but we could have done this different bit. We could have doubled, and then instead of it being 9 over 40 on the top, it could have been 9 over 10, and we could have subtracted 0.9, and that would have worked. Let's just double check that works. Yeah, still get the same as 1.5 meters. Last thing that it says is criticise this model with respect to the motion of the ball as it continues to bounce. We could say, which I think you said at the very beginning of this, a ball will eventually come to rest.
Yeah.
This model predicts it will never come to rest, okay? So realistically, the ball will eventually stop bouncing and come to rest. The model doesn't predict this.
That it will never stop bouncing. So you track it, it will never go above 1.5 meters.
Yeah, it's interesting that I think if you asked someone this question, you'd probably expect it to be a lot higher than 1.5 meters, especially if you're like, well, every time it keeps bouncing, it's basically not moving up and down anymore, because if it's quartering each time, it's going to get very small very quickly. But each time you keep adding on that small amount, you could add it on as many times as you like. It's never going to get above 1.5 meters. And this, if this kind of stuff like intrigues you or interests you, number one, you can go and watch YouTube videos about it. Like Numberphile is really good. Sorry?
Can you put that into a series?
Can I put what into a series?
The formula, or not formula, but that form to series. Or is that what S is?
That is the formula for the summer series. We will prove that in year 13. We just won't do that yet. If you're interested in this idea of like infinite things, that's probably a good sign that you should take maths at university, because that's what a lot of it's like. It's looking at like the ideas behind infinities and much more like philosophical kinds of questions as well. But yeah, that bit that's in yellow there, the formula for the sum of an infinite geometric series, that is something you have to just take my word for it now. And then in year 13, probably they won't do it for a couple of months. We'll do a proof of it. And when I do that proof of it, I'll send the video link to you so you can see what that proof of it looks like. But it's pretty simple, and we could do it now. So there's only 1 or 2 questions like this in the exercise book, so we'll have a look at it, okay?